Hi, my name is Tahera, and together with my co-author Wanggang, I will present our work on a Bayesian approach for quantifying data scarcity when modeling human behavior via inverse reinforcement learning. Computational modeling approaches can help us study and understand people's behaviors by formalizing the behaviors into models. And we can explore such models by simulating situations that people find themselves in and predicting the actions that they take in those situations. Recently, inverse reinforcement learning or IRL has emerged as a viable computational modeling approach for capturing, exploring, and predicting such behaviors. Unlike reinforcement learning algorithms that compute an optimal policy given known rewards, IRL algorithms estimate an unknown reward function that could have led to human behavior, and they do so by learning from historical behavioral data. Such data can come from people's personal devices, their wearable devices, as well as from smart environments. Then the existing IRL methods convert such data into behavior instances, which are sequences of situations that people find themselves in and the actions that they perform in those situations, to then build probabilistic models that capture the inherent uncertainty in people's behavior. So, given these kind of models, the question is how many behavior instances do we need to collect to accurately estimate the parameters of these models? Not collecting enough data or under collection results in high uncertainty of model parameters and predictions. And collecting more than necessary amount of data or over collection places undue burden on the participants and wastage of precious resources and time. So here we present a sample size determination method based on uncertainty quantification for a specific IRL model of human behavior in two scenarios. Pre-hoc experimental design conducted in the planning stage before any data is collected to guide the estimation of how many samples to collect, and post-hoc dataset analysis performed after the data is collected to decide if the existing dataset has sufficient samples and whether more data is needed. And we will illustrate our method on an example of modeling behavior of people with multiple sclerosis or MS using IRL. MS is a chronic disease of the central nervous system, and in this use case, researchers and clinicians want to study behavior of people with MS by forecasting their symptoms and their functioning using an IRL based computational model. They need to collect data that describes behavior instances of people with MS. For example, situation features may describe who those people are, such as their gender and age. They could describe what time of the day this data was collected. So in this particular case, when the person with MS just woke up, then to forecast their fatigue and functioning, we need self-reported symptoms at this time step. And similarly, defined features describes the actions. So for example, we may indicate if they recorded their pain and their fatigue and their activity level at that time step. And then once they perform that action, they move on to their next state, here morning, and they perform another action and move to their next state, and so on for the rest of the day and end of their behavior instances. And then we can use such behavior instances to estimate parameters of a probabilistic model of human behavior. We can express this model as a Markov decision process where the states represents our situations, actions people with MS can take, the probabilities that a state starts a behavior instance, the state transition probabilities both estimated using a Bayesian network, and final probabilities of actions given situations which we estimate using an IRL algorithm by relating those probabilities to the reward function we are trying to recover from the data. IRL computes unknown parameters theta used to estimate the reward function R, where f is a vector features for action A that the person with MS performs in situation S. We hypothesize that the unknown parameters theta depends on the number of behavior instances used to train the model, where more data will provide a better estimate of model parameters theta.
Thank you, Tahera. Hello everyone, I'm Wanggang and I will tell you more about our SSD method. We present a UQ-based method for estimating how much behavior data to collect to obtain an accurate estimate of IRL model parameters. This informs our generalizable SSD framework that balances the gain and cost of collecting data for both pre-hoc design and post-hoc analysis. The main insight behind our method is that the probability of model parameters given training data can be updated from the prior P of theta to the posterior P of theta given D through Bayesian inference. The prior thus represents the before data uncertainty, and the posterior is the after data uncertainty. Then we quantify the shrinkage of posterior from the prior using the information gain based on the KL divergence. Since SSD is desired before data collection, D will not be available yet at this pre-hoc stage. Thus, we need to take the expectation over possible realizations of D to arrive at the final expected information gain, or EIG. We then adopt a Monte Carlo estimator using posterior samples generated from the Markov-Chain Monte Carlo algorithm to estimate the EIG. This figure shows relationship between expected information gain and number of data samples. We hypothesized a common trend, a sharp increase of the expected information gain followed by a gradual flattening of the curve. This is consistent with our intuition on the diminishing return of information gain as the total dataset size grows. Looking at the knee-like trend of this plot, the data sample sizes fall under too little data before the knee where EIG is still rising rapidly, potentially enough after the knee, or plentiful once it starts to plateau. In the pre-hoc experimental design, the model designer seeks to estimate the number of samples to collect. We propose a procedure to arrive at this number, where the experimenter needs to supply two parameters. The first parameter is the absolute maximum number of samples (ND-max) allowed by the resource constraints, for example, time, funding, number of people in the target population. And the second parameter is the target percentage of the maximum EIG that the model designer wishes to achieve, for example, 80%, 90%. In our use case, we choose those parameters based on a total number of 1,500 possible participants for a standard 7-day data collection study at a standard compensation of $200 per participant per week, which totals to a prohibitively costly budget of $300,000. This equals to ND-max equals 10,500 samples, and as a demonstration, we select P equals 80% as a reasonable target. So conceptually speaking, plugging ND-max, which should be somewhere in the green region, into our figure, we get EIG max, and then calculating 80% of the EIG max, we can get the estimated number of samples to collect. In the post-hoc dataset analysis, the model designer can calculate if the number of samples in their collected dataset is sufficiently large. By inputting ND-max into another procedure, they can compute the percentage P of the maximum EIG reached by the realized post-hoc EIG and compare it with some desired alpha level to see we have collected sufficient data samples to achieve our target EIG. We again plug ND-max into our figure to get EIG max. We can then calculate the EIG of the data that we have already collected, and we get the percentage of the maximum EIG that has been reached. So to validate our model, we use the existing MS dataset containing 749 behavior instances. We split this dataset into two subsets: simulated pilot study dataset with randomly selected 6 participants to initialize our EIG calculations in the pre-hoc, and post-collected dataset with 101 participants to simulate the post-hoc analysis, and use the same parameters from our use case budget. And then we validated that our method is robust for different number of MCMC steps and different priors, which all result in similarly shaped EIG curves and similar number of recommended samples, so we simply pick one of the priors. For pre-hoc design, we compute the required sample size for 80% of maximum EIG to be around 807 samples. And our post-hoc analysis showed that the 707 samples we have collected is sufficient. Note that the estimated sample size in pre-hoc design and accepted sample size in post-hoc analysis could be different because we have more data to better estimate the EIG in the post-hoc than what our prior gave us in the pre-hoc. So to summarize, a key novelty of our approach is the use of Bayesian inference for guiding SSD in IRL context. We encapsulated our method in two simple functions, one for pre-hoc design and one for post-hoc analysis. Our method is completely general for any IRL model without any requirements on the domain, dataset, and feature choices. In the future, we plan to apply our SSD method in different human behavior modeling domains and explore the trade-off between information about model parameters and burden on participants. Our Bayesian formulation of IRL enables study of human behavior under uncertainty. Thank you.